All right. Hello. So as promised, today we are finally going to talk about the infinite square well potential. And this will be our first example of a quantum system that you can really get your hands on and think about and hopefully write about in your paper some. But I realized before we do the infinite square well, there's one more thing we have to do, and that is talk about separation of variables and stationary states. So first, let's talk about separation of variables. In PDEs, one of the things that you do sometimes to solve a differential equation is this thing called separation of variables, where you take, for example, a function of two variables, and you suppose, with no justification whatsoever, that it can be written as a product of a function of each variable independently. So we'll take the wave function and we'll assume that it can be broken up as a product of little psi of x and t of t. And I will, as a convention, use capital psi for the full wave function and little psi as a function of only x. Now, obviously, this is a ridiculous assumption. There's no reason that you should assume that the wave function is actually a function of this type, but it'll turn out that we can use the separable solutions, the solutions of this type, to sort of get a general solution by superposing all the solutions like this. Okay, so we'll suppose that psi of xt is a function of the form little psi of x times t of t. And then what this does for us is it lets us, well, one thing is it turns the partial derivatives. So if I take the partial derivative of psi, for example, with respect to t, it now this is just psi of x because it's constant with respect to t, and it's the psi of x times the total derivative of t with respect to little t. And similarly, d psi by dx is just t of t times d little psi by dx. So it turns the partial derivatives operating on big psi into total derivatives operating on these single variable functions. So that's one thing it does for us. And we'll see that it actually transforms the Schrodinger equation, which is a PDE of two variables, into two ODEs of one variable. And that's quite nice. Remember, we talked about before that we can identify the operators E with IH bar d by dt, because, and we gave an example of the free particle wave function. So if you operate on the free particle wave function with the first time derivative, you get something that looks like E times the wave function. And similarly, if you operate on a free particle wave function with the space derivative, you get something that looks like P times the wave function. And it turns out in quantum mechanics, we can basically identify the energy with this operator and the momentum with this operator. So these equalities. And that makes the Schrodinger equation really easy to write down because it's just a rephrasing of this relation E equals P squared over 2m plus V. And then, right, we can just write it as the operators. I just replace E with this operator and I replace P squared with this operator. And that's it. That's what the Schrodinger equation amounts to. And then also I would like to draw your attention to one thing is that we are supposing the potential is only a function of x for this whole video. So none of this will work if our potential is time dependent. In general, it'll be too hard to solve the Schrodinger equation for us in the cases where the potential is time dependent, and you don't see that often. But yeah, it is important that v is v of x. But yeah, okay, Schrodinger equation, I guess I should put a psi in here because we're actually operating on the wave function. But if you operate on the wave function, these two operators are equal, and so they operate on the wave function, they return an equal, they return this equality. All right. But now we'll see where separation of variables comes in. if I have that psi, big psi, is equal to little psi times big T, then when I plug it into the Schrodinger equation, I get total derivatives with respect to x and t, and this is the expression that I get. I get IH bar psi dt by dt is minus h bar squared over 2m d squared psi by dx squared t plus v psi t. And then if I divide everything through by big psi, so divide by little psi of x times t of t, then you obtain this expression at the bottom. And this is where the magic happens. If you'll notice, once I've divided out by big psi, what do you notice about the left and the right-hand side? They depend on different variables. This only depends on t. This only has a t dependence, and there are no t's on the right-hand side, and the right-hand side only depends on x, and there's no t's on the right-hand side. And so the only conclusion that we can draw from this is that both sides must be constant. So both sides constant. Yeah, so my tablet is broken and I'm trying to like write while looking at the screen, and it's very trippy and it's terrible. So I'm going to attempt to write the least amount possible. I tried to pre-write as much as I could. Okay, so if both sides are constant, I'm going to name this constant E for reasons that will become clear in a minute. But both sides are constant. That means that I have two ordinary differential equations. So I've transformed our PDE, the Schrodinger equation, into two ODEs by doing separation of variables. This is actually a pretty useful and powerful technique. But unfortunately, the solution will be a little bit sophisticated. We'll see it in a second. But okay, let's solve these two ODEs that we've obtained by setting the two sides equal to a constant. If we set the left-hand side equal to the constant E, then we can use what you probably called separation of variables in your ODEs class, where I just take all the little t's and I put them on one side, and all the big t's and put them on one side, and then I integrate both sides. So that's what I've done here. I've taken all the big t's, I've grouped them together. I've taken the only little t we have is dt. And I integrate this side with respect to t, and this side with respect to big T. And I get log t equals et over IH bar. I guess plus a constant too. And then I exponentiate both sides. I get t equals c e to the minus iet over h bar. Sorry, I changed my 1 over I to a minus I. But that's what I get. That's what I get for big T. And then on the right-hand side, if I set this equal to E, and then I multiply back through by psi, multiply everything by psi, what's that? All that is the time-independent Schrodinger equation that we talked about super early on in the semester. So that's the time-independent Schrodinger equation. We won't solve this right now, but the solutions to this are time-independent psi's. So the solutions are time-independent. And they're functions of the form psi of x, not psi of xt. As we also talked about a little bit before, the solutions are actually the eigenfunctions of the Hamiltonian, where the Hamiltonian is this this operator minus h bar squared over 2m second space derivative plus v. So the stationary states, I guess these aren't the stationary states, these are the time-independent parts of the stationary states. Those are the eigenfunctions of the Hamiltonian for the specific potential that you're working with. But these are the functions that satisfy the eigenvalue equation, the time-independent solutions to the Schrodinger equation. And then, okay, so now we have, if we have that capital psi is equal to little psi times t, and we've solved for t, that means that if I solve for little psi, I solve the time-independent Schrodinger equation, then to get the time-dependent solution, all I do is I tack on this factor of e to the minus iet over h bar, and I have the time-dependent solution. So that's pretty great. These are what are called stationary states. So they're the solutions that look like this. And why are they called stationary states? The reason is because the probability density is actually also time independent. So one reason is because it's completely determined by this little psi of x that's time independent. But then if you compute the probability density, you compute big psi star, big psi, you get psi star, little psi star, e to the iet h bar, and little psi, I to the minus iet h bar. And these complex exponentials cancel each other out. So what all you get is a time-independent probability density. It only depends on x. So it doesn't matter when you measure this system, if it's in a stationary state. And then the other reason, sort of the second most important reason we care about stationary states is because they're the states with definite total energy. You can see this by computing the variance of the Hamiltonian. I'll leave this as an exercise for you to do, but if you compute, if you remember how to compute the expectation value of an operator, what you do is you sandwich it between big psi star and big psi. But then again, the complex exponential parts of this will commute, and so you can cancel those out. So you'll actually just get little psi star, h psi. And you know that h psi is e psi because of the eigenvalue equation. And so you'll see that the expectation value of the Hamiltonian is e. Okay, and then, of course, why did we choose the separation constant E? Obviously, because it's the eigenvalue of the Hamiltonian, and that's what the energy is. And what we'll find when we actually do this, solve this for a potential, in particular, we'll do the infinite square well today, is we'll see that we find a bunch of solutions, in fact, infinitely many, and they're indexed by natural numbers n. And they'll each have a distinct and actually discrete energy eigenvalue, and they'll satisfy this eigenvalue equation h psi n equals en psi n. And then that means we have n stationary states. So each of those we'll call capital psi n, the nth stationary state. And then this is the magic of separation of variables, is that a general function can be written as a linear combination of these separable solutions or stationary states. So it will be true in quantum mechanics that any wave function can be written as a linear superposition of these eigenfunctions, the psi n's, times these little wiggle factors, e to the minus iet over h bar. So we'll do that. I'll actually show you how to compute the coefficients of this next time. And we'll do maybe on a problem set an example of how to compute these CNs. But this is this sort of the study of how to write a general function as a linear combination of other somewhat simpler functions. This sort of gets into Fourier analysis when we do this. And the fact that you can do this is a little bit harder to prove than just if I just tell you that you can. That's good enough for now, and I'll show you how to compute the coefficients. Okay, but I'll do that next time. I'll stop this video, and I'll record another one on the infinite square well in just a second.